Good morning, or evening, really, wherever you are. Yeah, that doesn't matter. Welcome to our first video of Unit 3, History of Atomic Theory. I'm breaking apart my units into smaller videos. Hopefully this will help you more, keep you more interested, and make it a lot likelier that I will keep up with the videos. That's kind of the real thing. Anyways, though, welcome. So this unit is on atomic theory. We are trying to figure out, ultimately, how in the world we know / think what we think we know / think. Anyways, basically, where did our information come from? Starts me with a guy named Democritus. And yes, that is Democritus. Democritus is very famous for, well, laughing. He's actually quite called the laughing philosopher, which has nothing to do at all with anything. But more importantly, the beginning of our modern atomic theory occurred with Democritus around 400 BC. That is like 400 years before Jesus. So that means technically when Jesus was growing up, he probably had a brief lesson on chemistry. That's kind of awesome now that I think about it. Anyways, Democritus described atoms as being indivisible and indestructible. Basically, very, very tiny things that we can't break down any farther. Wow. Partially true. I mean, A for effort and all. We have definitely improved this. For example, about 2100 years later, a guy named John Dalton. Now, let me explain. There are people who have did stuff before then, but we mainly care about John Dalton. He expanded Democritus' work and posed his atomic theory, which we commonly call Dalton's atomic theory. I know, rather boring name, but nonetheless, that's what we call it. He has four main points. First off, he says all elements are composed of tiny invisible particles. Kind of like these. Now, that is similar to what Democritus said, and we're great. He did say they're indivisible, and he actually called them atoms instead of just tiny things. Dalton also said that atoms of the same element are identical. He said the atoms of one element are different from those of any other element. Now, for that, we're looking here. Notice they are apparently weighing the same thing. I'm trying a stylus, and it's kind of not really working. But he said atoms of different elements are different. This is where he's actually a little false. Well, we've learned about a concept called isotopes, which is where you can have atoms of the same element with different numbers of neutrons. So he was kind of right, but not completely. His third point, though, was that atoms of different elements can physically mix together or chemically combine together in simple whole number ratios to form compounds. Those are these. He basically said things can either be put together. For example, if we mix, I don't know, iron shavings and copper shavings. I don't know why you'd ever do that, but you could. You can mix them together, and it's totally okay. You can also combine things together like hydrogen and oxygen and get water. That's basically what Dalton's saying. They're not just small things, they can actually combine to form bigger things. Lastly, he says chemical reactions occur when atoms are separated from each other, joined or rearranged in a different combination. Now, typically the main thing we care about, though, is this last part, which is summarized by us trying to break an atom but failing. Atoms of one element are never, ever, never change into atoms of another element as a result of a chemical reaction. Meaning if you start with two hydrogen atoms, you're going to end with two hydrogen atoms, not three hydrogen atoms or one and an extra carbon or something. You cannot destroy atoms. There you go. That's John Dalton. For the most part, he was right. But we are going to now try and draw a picture of what an atom would look like according to Democritus and Dalton's atomic theory. Well, you didn't hear anything about what we call protons, neutrons, or electrons. So they basically said they're really, really tiny, small things. Hopefully, you have guessed this by now. An atom, according to them, we're going to see if I can draw this, would be that. Hey, totally worked. But that's an atom. Really, really tiny, small thing. Now, I know that's huge, but just stick with me. Pretend we zoomed in crazy, stinking far. That's an atom. Really boring and really wrong compared to what we know today, but we'll go with it for now. For example, about 100 years later, well, a little more than that, a guy named J.J. Thomson. Ooh, that's a picture of J.J. Thomson. Ooh. He proved that basically Dalton's theory was not enough. He said that atoms are divisible, meaning you can actually take an atom, we'll pretend that's a circle, and you can break it apart. Okay, I just need to give up drawing. Like, you can actually go smaller than an atom. That's mainly what he's looking at. Not saying let's break atoms, that's a nuclear bomb, and that happened a couple 100 years later. Okay, actually about 30 or 40. Anyways, he used a cathode ray tube, which this is a cathode ray tube, to prove that there is a small negatively charged particle in an atom. Today we call that particle an electron, and he is officially credited with discovering the electron. Now, let me show you what this means. You've got this like battery charge thing and it's cord to wires. That is called a cathode ray tube because it shoots a ray of cathodes. Now, the main thing we got to care about though is it shot a ray of particles, some positives, some negatives. He did move this to realize there's some kind of positive particle, but we're just not going to really go into that. What he noticed though is that the negative particles he had went towards the positive plate. And he realized, okay, wait a second. These things are separating. These things are splitting. There has to be more than just one type of particle. Otherwise, they all would have just gone straight. But apparently they're attracted to something else. This is like you shooting, water at your friend and half the water going to one friend, half the water going to another. You're like, okay, that's just weird. It should have all gone straight. But it didn't. So he said, all right, there's something down there. He called a negative particle. We eventually know that as the electron. Thomson then took that atomic idea further and hypothesized that electrons were inside the atom, and he said they're just kind of evenly distributed. He didn't really care how, he just said we have electrons stuck inside this positive matterness. He called this a plum pudding model. I don't think I have a picture of plum pudding, but imagine like a chocolate chip cookie where you've got chocolate chips just stuck in the cookie. That's kind of what he's saying. The chocolate chips aren't moving. The dough's not moving. The dough has a different taste than the chocolate typically. And he's saying you've got an atom. All this pink stuff is basically positive material, and the electrons are kind of just stuck in there. That's called the plum pudding model. Now, that is an improvement, still not there. So let's draw another picture. Let me see if I can get a circle this time. I'm going to try not to fill the circle. So if this doesn't work, well, whatever. So, yeah, we got a circle. And I don't think I'll be able to add shapes correctly, so whatever. That's an atom. And then we've got a little... Come on. Trying to draw with this. Oh, drawing white on white. So, little electrons all in it. So we're getting there. That's closer to what we're knowing, but again, we're still not there. But if we're going to take any time, by the way, to pause the video, rewatch, relearn something, you are expected to know these models, who did what, how we figured out we needed to expand the model. Feel free to rewatch and make sure that you've got a pretty good idea of what's going on. All right. So, a little bit later, a student of Thomson's, Ernest Rutherford, disproved his plum pudding model. Now, to be honest, his assistant actually did this. Thomson's actually doing this experiment. He's like, we're not getting anywhere. His assistant said, all right, whatever, I'll clean up. Sat there for a bit, started, pulled out her iPhone, started playing Clash of Clans or something, and started noticing, wait a second, this thing's doing a bit more than we thought. Called him back over and said, okay, that's strange, something's wrong. And thus they disproved the plum pudding model. Now, how did she do that? Well, I'm about to tell you. And for the record, no, she was not on her iPhone. Like, cheers. Come on. All right. Rutherford performed an experiment with gold foil. Yes, he had gold foil, like aluminum foil, but gold. So I don't know how he got that. But he found that light bounced off at angles completely unexplained by the plum pudding model. Now that's great. It normally kind of makes sense. Let me talk about this picture. He said, all right, let's take a laser and shoot it at the gold foil. And by the laser, the light that they would typically see reflecting, you would imagine it over here. Now, I know that doesn't really make a whole lot of sense because typically light bounces back at you. This is just kind of giving you a picture of pretend it would go through it. So it would go here, and he's like, all right, cool. But then his assistant noticed, wait a second, what are these? Like, why is there stuff bouncing off? This is like, um, Thompson actually, or Rutherford described it. This would be like shooting a artillery shell at a piece of paper and it bouncing back and hitting you. He's like, this doesn't make any sense. Or you throwing a tennis ball to your friend or something, and halfway there it bounces off something and you go straight to the ground. You're like, wait, did it just bounce off air? That doesn't make any sense. Or, you throw in a ball to your dog and halfway through it just going off to the left and you and your dog are just confused. It doesn't make sense according to the model they were using. So I said, okay, apparently electrons are not stationary, meaning they are apparently moving. They're not just sitting still in a positive material. Something else has to be going on because according to what we expected, that is not nearly what's happening. We're having other things going on. So he developed his nuclear model. He theorized that all the protons and neutrons, which, by the way, we actually don't know neutrons yet. You can use that phrase, but right now he just says all the positive mass is actually what he's knowing. That's why this picture just says positives. He says they're in a small, dense region in the center. He called that the nucleus. He said the electrons were kind of scattered around in the area, taking up the majority of the volume. Now, when I say majority of the volume, this is like you've taken a marble and this has taken up a 1 to 2 feet sphere around it. Like nucleus compared to electrons is tiny because they take up so much space. He didn't quite get that detailed, but modern day the electrons take up a lot more space than the nucleus. But anyways, he's saying they're not just stuck in there. They're moving around somehow. I'm not really sure how. I just know they're moving. And they're not just sitting next to the protons. That's the nuclear model. So, again, a picture. Nucleus with positive charge in it. And electrons outside. Taking up most of the space. Now, if you want, sometimes people put like, little orbity looking things. That's not fully him. It's like some people attribute this with him, some people don't. If that helps you remember that the electrons are outside moving, go ahead. All right. Now, he is honestly in a pretty good track. We haven't gone much farther from that, except we had this minor issue. You see this metal? Metal is not normally that color. If you see that metal, hopefully by now you've learned don't touch the metal. Now, it's not just because we painted it a pretty color, it's because that metal is hot. You don't touch hot metal, it starts changing colors. So, his nuclear model doesn't really explain that. Now, you're probably thinking, why do we care about colors of metal and electrons? Well, turns out around Rutherford's time, that's what people did. They took random phenomena and said, explain science, go. And they kind of realized his model doesn't explain this. Why is there a change of color with an influx of energy? Well, we had a guy named Einstein who threw a couple theories at us, and he was pretty smart, and we had a couple other guys. But eventually, that mainly led to a guy named Niels Bohr, who just looks scared of the photographer or something. He made what's called the Bohr model, or sometimes just called the shell model. This states that electrons orbit around the nucleus in fixed circular paths called shells. Now, this is a Bohr model. You've probably done this in 8th grade and cringe in terror from this. Don't worry, we're not doing a whole lot of this. Key things you got to know. Nucleus in the middle. Circles around it. And electrons are on the paths. You will not find them inside. No, I just realized. I got a lightsaber. That has nothing to do with chemistry, but whatever. So, this is going to be obnoxious, but we're going to try it for a bit. This... That's right, I got a purple lightsaber. Anyways. So, electrons are not found inside the paths. So, they're not here, they're not here. That is really not useful. Sorry, guys. Okay, they are not here, they're on the paths. In fact, actually, if they need to change the paths, he said, all right, it requires a quantum of energy. Now, it turns out, if you take this idea further, he says, all right, if you'd use enough energy, electrons will start at one level, be released to a higher level, actually start at one level, be released to a higher level, and actually emit a photon of energy. Basically, use up the energy and then shoot off whatever's left. And then they'll fall back down to whatever state they had. That is actually what he says explains those colors. You're giving electrons energy, they're going to higher levels, but they can't stay there because that's just not where we'll get there, why they can't stay there. It's not their ground state is what we call it. So as they're falling back, they're releasing off energy. I almost imagine a kid on the top of a Ferris wheel saying, "This is a really pretty view," and then as it's coming down, he's like, "Wait, but I want to see more. I want to see this." Or some people imagine a firework that goes up, releases energy, and falls back down. So that's what kind of the Bohr model says happens with those colors. Fortunately, we are typically very good at drawing Bohr models. So I'm going to get a circle. We have a nucleus, and hopefully you're freaking out saying, "Wait a second, Mr. Booth, I thought you said, just a black circle is bad." Well, don't worry. Okay, now you can worry. Seriously, computer, iPad, you have one job. I'm trying to draw a plus sign, by the way. Yay, plus. Okay, so we have a positive nucleus. Again, not a whole lot of mention of neutrons or protons yet. Right now, we're kind of just thinking that circles, like nuclei, just have positive stuff in it, and that really backfired. Alright, whatever, I guess I'll just draw this. So, we have a positive nucleus with shells all around it, and the electrons are found on the shells, not in between. There you go, Bohr model. Alright, finally, welcome to basically modern atomic theory. I know the entire point of the video. A guy named Erwin Schrödinger. So finally, in 1926, we have our actual modern atomic theory guy, presented by this guy with crazy hair, Erwin Schrödinger. He proposed a mathematical equation that actually describes the location of an electron based on probability. Now, there's a few scientists that actually got in his way who actually looked at Bohr and said, "Okay, we have this issue. You can basically either tell me where the electron is or how fast it's moving, but you can't do both." And Bohr's like, "Well, what are you talking about? My model seems to work." They proved it wrong, and that's about where Schrödinger said, "Okay, apparently we can't find electrons literally by saying, here's their geographic coordinates, but we can say they're somewhere in this area." Kind of a loophole in science, I guess, if you will. So, as I said, recent scientists had shown that the location of momentum could not be determined. So he said, electron locations could be narrowed down to orbitals. So basically he said, we got a nucleus, and we have this cloud of electrons. And he's saying electrons are somewhere in there. Now, he does actually start narrowing it down to more like saying you're going to find some electrons in kind of this area. You'll find some electrons taking this path, like they'll actually be taking certain paths or areas with certain shapes. We'll talk about that in our next video. But he basically narrows it down again to probability. Now, he is using orbitals. He defines an orbital as a region of space in which there is a high probability of finding an electron. Remember those shapes I talked about? These are the types of shapes you can have. You can have things that are spheres. You can have things that are like three-dimensional figure eights. You can have things that are, I don't know what those are. I don't even know what these are too. But he said basically you can have different shapes of areas so that you can find them. I really don't know how he did this. But this is our current version of atomic theory. We find electrons in certain shapes, in certain areas. We can say, all right, there's going to be 2 electrons somewhere here, 2 electrons here, a few electrons here, and we can place and configure all our electrons around an atom to say this is where they would be located. Are we narrowing it down to saying it's standing right here and in 5 seconds I can use a pair of tweezers and flick it up? No. But we can say it's going to be somewhere nearby. That is our atomic theory. And one last little tidbit of information. In 1932, a gentleman named James Chadwick expanded this theory once more And he realized that there is apparently a neutrally charged particle. And he calls this a proton. Now, you're thinking, why does this matter? Well, originally, remember, our nuclei looked like... Oh, come on. That. And he's saying, well, apparently, that's not all just one thing. You can break up the nucleus. And now, it's more some positives, but you also have some neutrals, some blanks, if you will. In hindsight, I probably could have just pointed you at the picture. That actually would have worked better. So he's saying now that there are protons and neutrons, which are all surrounded by electrons. So thus, we now have our 3 subatomic particles. It's not just a tiny blob of tiny stuff. It really comes down to protons and neutrons surrounded by a cloud of electrons. And this is kind of a summary of... wow, my writing did not show up. I'm sorry, guys. I'll put those in. Sort of some of the details we found. So this top one, my stylus is not liking me, are my electrons. The bottom one are neutrons. And basically, sometimes you'll see electrons as E negatives or protons P positives. Electrons typically have a negative charge, protons are positive, and neutrons are neutral. Relatively, protons and neutrons weigh about the same, but electrons are pathetically tiny compared to it. So they really just don't weigh anything compared to them. And if you actually wanted their actual mass, I'm sorry this table is not showing up well, but that is actually their mass. This negative 28, by the way, should be a power of 10. I will fix this at a later time, but right now, I don't care a whole lot in your test, so to be honest, you don't need to care about this either. So at some point, I will fix it, but until then, all you need to care about is electrons are tiny. There you go. Thank you for watching. Yeah, have a good evening.